This video is going to cover Euler's method. So we've learned two ways to approximate. So we've kind of gone out of order, but we've learned two ways to approximate values for unknown functions. The first way that we learned was using what we call that tangent line approximation. So I'm going to just do a quick sketch really quickly. That is a terrible line. I apologize. Not much better. But let's say we had a coordinate system. And we had some function for that on that coordinate system. So let's say we have some nice polynomial here. Okay. Let's say we know the rate of change, so we know dy dx. If we have a point, let's say that point right here, let's go with that one, we can use a tangent line. We're going to call this our x and a y specific. If we look at that x and that y, we can use a tangent line approximation to evaluate some other point on this function close to that point by using our tangent line approximation. So if we actually sketch in our tangent line, we get something that looks like this. And I know this is not perfect, but good enough for our demonstration. So this tangent line would probably be good to approximate anywhere between here and here. I would say it's a good approximation. But if I wanted to approximate this point, we can see that our tangent line is pretty far from that point. So that's not going to be a very good approximation. So a mathematician with the last name of Euler, of course, started looking at if all we know is a starting point and the derivative to a function, how could we use that to, in fact, approximate a value that's far from that point of tangency? So what he decided to do was to not use that tangent line to approximate that last point that I have here, but he decided to actually look at using this tangent line to approximate maybe this point right there. Okay, so that would be a good approximation. But if we reevaluate and create another tangent line using our tangent line that we have, because we know that slopes being the same represent parallel, so we'd have this idea of another tangent line that's going to be parallel to the actual tangent line for this function. And if you can see that distance here, that distance is getting smaller. So he said if we keep reevaluating this and do multiple tangent lines, so I'm going to choose a different color. So let's say now we use the blue tangent line to approximate that value. We get this idea of another parallel tangent line. Okay. And we can see that we're getting closer and closer. In fact, the more that we break this up and the more partitions that we take, let's say I use that point right here and created another tangent line that's parallel. If we keep doing this, we're going to get closer and closer and closer to the point that we want. So Euler said if we create multiple tangent lines and do a repeated tangent line over and over again, we can get a better approximation than using that single green tangent line that we started with. Okay, so let's kind of see what that process looks like. The biggest thing to remember is all this is a repeated tangent line approximation. So let's kind of get into it. Okay, so another way to approximate it, again, this is a tangent line approximation. So it all starts with, in fact, our tangent line. We started by actually rewriting our tangent line, and this is the one that we use in class by adding that y1 to the other side. And this is the one that we're used to using in class, so our tangent line approximation. So here's the equation for the tangent line. If we think about this, that x minus x1 represents that idea of change of x. And we first saw that idea when we were talking about our Riemann sums and things like that. So I'm just going to replace this with this idea of change of x. So x1 minus x2, of course, is our change of x. And if we think about this, we can use this equation right here to figure out what we call a new y value. And we're going to do that by taking a y value that we know, we're going to call it the old y value, plus we know that m in this class is our derivative. So if we know a derivative and a point, we're going to use that derivative to replace m and multiply it by that change of x. So with a little bit of alteration, we get a brand new equation of a tangent line, but it is really just the same equation itself. So things that are going to change, because we're reevaluating and readjusting our tangent line, our derivative is going to change as our x and our y changes. Okay. But our change of x, we're going to actually determine what our change of x, and that change of x is going to stay the same for all repeated tangent line approximations. Just like with Riemann sums, our change of x stayed the same with the exception of dealing with a table. Okay, so there's 4 things that we need to know up front in order to find the equation of a tangent line and apply Euler's method. That first thing is we need the differential equation. And the reason we need that, I'm going to get a different color here, is because this is going to give us our slope in our tangent line approximation. Okay, so we're going to need that dy dx. Okay. We're also going to need a starting point, a known point on that function. Just like with the graph that I did, we knew a specific point, that x and that y. So we're going to be given a starting point. And then the next thing we'll need, the third thing, is this idea of what we call step size. How many different partitions are we going to take and break it up into? Most of the time, you'll see 2 and 3, but we can do multiple partitions just like we did with Riemann sums. And that idea of the change of x comes from that same equation that we did with Riemann sums, which is just our change of x is equal to b minus a over n, where b itself is the end point, the point that we want to approximate. Our a is the start point, okay, what value we have, and then n is going to be our number of partitions, or we call them the number of steps that we're going to take, okay, how we're going to split it up. And then, of course, 4, the last thing we need is what we're trying to approximate. Okay, that idea of what we're trying to approximate gives us our b value in our change of x formula. Okay, so let's kind of do a problem, kind of see what it is, or what it looks like. Okay, so it says let y equals f of x be the solution to the differential equation dy over dx is equal to x minus y minus 1. So with these differential equations, you're going to get some that we can solve, but then you're going to get some like this one that is not solvable or integratable because of the implicit variables in the problem. And this is where we would go to our approximation methods. Okay, so that's kind of where this method comes into play. So the first thing, of course, that we need in our list is a dy dx. And we do have that. So our dy dx for this problem is in fact x minus y minus 1, an implicit equation because our x's and our y's are mixed. The second thing we're going to need is our starting point. And that starting point is often given in function notation. So that starting point right there is our x is 1 and our y is negative 2. Okay. Third thing we need is the change of x. And that's something that we're actually going to have to actually calculate. Okay, so I always skip 3 and go to 4 because 4 is going to give us our n value. And our n value is, of course, the value that we're trying to approximate, which is at f of 1.4. So we're trying to find f of 1.4. Okay, so our a value is the starting point. Our b value is the ending point. That's why I kind of skip over and go to 4. So 1.4 is our endpoint, the point we want to approximate, minus our starting point, which is 1. And we're going to go 2 step sizes, and that means my n is 2. So I get 0.4 over 2 equals 0.2. So my change of x is in fact 0.2. The next thing that I do so that I can organize my work, because I am going to be doing the same thing over and over again, and I want to make sure that I get the right things everywhere, is I create a table, okay, for my x's and the y's that we find. Our table always starts with a known value, so 1 and -2. To get our next x value, we're going to add the change of x. So if I add 0.2 to that, I'm going to get a 1.2. Okay, if I add a 0.2 again, I'm going to get a 1.4. And I should be at the point that we're trying to approximate because we did say 2 steps. So from here to here is 1 step, and then from here to here is another step. Sorry, there we go. Okay, so what I'm going to do is I'm going to use that first point to help me approximate what the y value is at 1.2, just like with the tangent line approximation. So the first thing that I'm going to need is, in fact, my slope. I have the point, which is 1 comma -2. I need the slope at that given point. So here we are, so at 1 comma -2. And all we're going to do is plug those values into the appropriate x's and y's in our differential equation. So our differential equation was x, so 1 minus my y value, which was -2, minus 1. Now all I'm going to do is calculate that. So 1 minus -2 would give me 3. 3 minus 1 would give me 2. After that, it's about setting it up in our tangent line approximation. Our tangent line approximation said the new y value at 1.2, and actually I'm going to use this notation really quickly to kind of help us keep organized. So the y value when x is 1.2 is approximately our y value before, which is this y value that we know, so -2, plus my slope, which is right here. That's our slope, and our x minus x1, or our change of x, which we calculated to be 0.2. After that, I'm just going to calculate what this is. So -2 plus 0.4, which gives us -1.6, which means that this value here, when x is 1.2, our y value is approximately -1.6. So now I know a new point on my graph, so I'm not going to use this point, so I'm going to scratch it out, and I'm going to do the exact same process with that new point, starting from the top. So I'm going to use point 1.2, comma -1.6, and I'm going to calculate what my derivative is first at this point. Okay. Same thing like I did before, all I'm doing is going back and plugging into the differential equation. So 1.2 is our x minus my y value, which is -1.6 minus 1. So if I do that, 1.2 winds up being plus 1.6, so 2.8 minus 1, which gives us 1.8. Now you can do this in decimal form and fraction form. It really doesn't matter, just depending on the situation. So I kind of switch back and forth depending on what my change of x is. Okay, so then all I'm going to do to figure out what y of 1.4 is to do the exact same thing. Start with the y value that I know, which right now is -1.6, and that's the y value that we're plugging in here, plus my slope, which is 1.8, times my change of x, which was still the same, so that change of x doesn't change as we go from problem to problem. So if I do that calculation, sorry, those should be approximates, I get -1.6. 1.8 times 2 gives us 0.36. Okay, if you have trouble multiplying with decimals, just forget about the decimals. 18 times 2, which is 36, and then count your decimals over just like you did when you first learned how to multiply with decimals. Okay, so that's how I'm getting that 0.36. And when I calculate that, I get -1.24. So the y value for this x is -1.24. And what that means for us is that our approximation of f of 1.4, which is what we're trying to find, is approximately -1.24. 2, 4. And that's what that process of Euler's method looks like. Let's do another problem. Okay, at the top, again, I'm going to start with listing out everything that I need. So the first thing is I need my derivative, which happens to be dy dx equal to x minus 1. Then it says let y equals f of x be the particular solution. That just means that y and f of x are the same here to the given differential equation with the initial condition of f of 0 equals 2. So that right there gives me my initial point, my starting point. Use Euler's method starting at x equals 0 with 2 step sizes, so my n is going to be equal to approximate f of 0.6. So not my 3. My fourth thing that I need here is what I'm approximating, f of 0.6, which that lets me calculate my change of x, which is what I need. Where I want my endpoint minus my start point over the step sizes, which was 2. So if I get that, 0.6 minus 0. Sorry, not 0.2. I don't know where I got that from. Let me go back to that. Sorry, that should be 0 because our x value here, oh, let's undo that. Sorry, our x value here is 0. So once I do that, I wind up getting that my change of x is 0.3. So here is my table for this problem. X and y, our starting point is 0 and 2, not 0.2. If I add my change of x, I'm going to get 0.3. If I continue to add my change of x, I'm going to get 0.6, which is what I want to figure out. So there are my 2 steps. After that, now it's about doing all of the calculations. So I'm going to start with my point, 0, 2. That's the point that I know, and I'm going to find my derivative and in this case, our derivative is only in terms of x, so I can write the point just like I did, or I can just write the x value, because that's all I'm going to need. So when I plug it in, 0 minus 1 gives us negative 1. So our original slope for the first point is negative 1. Now it's about our tangent line. So y of 0.3 is going to be approximately, starting with my y value, which was 2, plus my m, and my m is negative, so that's going to be minus 1 plus a negative 1, times my change of x, which was 0.3. So really this becomes 2 minus 0.3, which is 1.7. And that means that this value is 1.7. My next step is to do the exact same process with my new point. So I'm not going to use that point. I'm at 0.3, 1.7. So if I calculate my dy dx at x equals 0.3, because I only need the x for this one, I get 0.3 minus 1, which gives us negative 0.7. So our slope is negative 0.7. So that means y of 0.6 is approximately, starting with my y value, which was 1.7, minus 0.7 is my slope, times my change of x, which was 0.3. And that means I get 1.7. 7 times 3 is 21, so move the decimal. So minus 0.21, which calculates to be 1.49. So this value is 1.49. And what that means for us is that our f of 0.6 is approximately 1.49. Okay. The next one I'm going to leave for you to try on your own at the end of this video. I'm going to go to that bottom problem, the one with the table. Now, the table ones are a little bit easier because it actually gives us our x values, it gives us our f prime of x's for all those specific x values, and it gives us that starting point. So just like I did before, I still create a table that I'm used to using. So first thing, of course, is the starting point, which is 3, 2. Okay, when our x is 3, our y values too. So just makes it easier to see. Still need to calculate my change of x. And I'm going to end up at 2.6 because that's what I'm trying to calculate. So that's my n value. So 2.6 minus 3. And then, of course, how many step sizes I want. And we're going to do 2 step sizes. That's what the problem says. So over 2, which means if we do this, we get negative 0.4 over 2, which is just negative 0.2. And you can see that in the steps, 3 minus 0.2 gives us 2.8, minus 0.2 gives us 2.6. So I already really have the x values that I need. But I do need that change of x for the formulas. Okay, so now we're just going to start with that process. Okay. So the point I'm using is 3, 2, or 3 comma 2, and our dy dx at this point. And they give that in the table in this right here. So our f prime of 3 is actually equal to 0.4. It's a little bit easier because we're not having to calculate what the derivative is. It's given to us. So really it's all about the calculation with these. So y of, and we're looking at 2.8, that's what we're trying to approximate, is approximately the y value from the previous point, 2 plus the slope times the change of x, right there. So if we do that calculation, we wind up getting 2 minus 2 times 4 is 8. Move the decimal over twice, 0.8, which gives us 1.92. So here we are at 1.92. If we want to fill out this table, 1.92 is where we're at. I just like my tables vertical versus horizontal. It just makes it easier for me. Okay, so my next step, my next iteration, or my next step will be using the point 2.8, comma 1.92. Okay, so I'm done with that point. So y to approximate 2.6 is approximately, oh sorry, I did not write down my derivative, so our dy dx at the point 2.8, 1.92. If we look to our table, that's that value right there. Okay. So then our y value, which is 1.92, plus our slope times our change of x, which gives us 1.92 minus 0.14. And after we calculate what that is, we get 1.78. So that's right there. And what that means for us is that our f of 2.6 is approximately 1.78. Okay, so that's kind of, it really is just our tangent line approximation over and over again. So try the previous example. Again, my answers are up in your online journal. If you have any questions, let me know.